Now we're going to start talking about the snake lemma, which is one of the most basic foundational lemmas in the theory of homological algebra. So it goes like this. We've got three chain complexes, U, V, and W, and some chain maps, I and P. Okay? And these are going to form a short exact sequence. So remember, that means that I is injective, P is surjective, and the image of I is the same as the kernel of P. And they're both supposed to be chain maps, right? So di is id, dp is pd. So then, we've got these maps, as we've discussed before. I lower star goes from the homology of U to the homology of V. P lower star goes from the homology of V to the homology of W. And so we've got these maps here. And this is on Hn, and this is on Hn minus 1, and this is on Hn plus 1. And you might hope that this sequence here was short exact, but that's not quite right. It turns out that it is kind of exact in the middle here. The image of I lower star is the same as the kernel of P lower star, but your I lower star is not necessarily injective, and your P lower star is not necessarily surjective. So this middle row is not actually a short exact sequence. But what happens is that there's this connecting map W, delta. Okay, so delta goes here. It goes from Hn plus 1W back to HNU, and then the next version of delta goes from HNW and Hn minus 1U. And it turns out that if we put in these deltas, then we've got this kind of long winding sequence, and it turns out that this is actually an exact sequence. So the image of P lower star is the kernel of delta, and then the image of delta is the kernel of I lower star, and then the image of I lower star is the kernel of P lower star, and so on. So the proof of this is quite long, but it's not that hard once you kind of get used to the general style of argument, but it is quite long. So we're going to break it up into a bunch of smaller steps. Okay, so the first claim was that we've got exactness at V. In other words, the image of I lower star is the same as the kernel of P lower star. Okay, we can state and prove this without saying anything about this connecting map delta, which is a bit mysterious that we'll have to deal with later. So proof of this, this sequence IP is supposed to be exact. So P composed with I is just equal to 0. That's, image of I is equal to the kernel of P, and that's enough to prove that P composed with I is 0. And so then it means that P lower star composed with I lower star, that's P composed with I lower star, which is just 0. And that proves that the image of I lower star is contained in the kernel of P lower star. So that's the easy bit. The slightly harder bit, suppose you've got we want to prove the opposite inclusion, that any element in the kernel of P star is also in the image of I star. Okay, so the idea is like this. We've got some element B in the kernel of P star, and you want to prove that it lies in the image of I star. So here, B, that's supposed to be an element in HNV. So that means it can be represented as square bracket little v for some cycle little v. So that's some element little v in Vn, with dv being 0. And our basic assumption is that P lower star B is 0. Okay, you're saying that B is in the kernel of P lower star, so P lower star B is going to be equal to 0. But P lower star B, that's just the same as bracket PV. So bracket PV is 0 in the nth homology of W. But remember, the nth homology of W is defined to be this quotient group, ZNW mod BNW. So to say that bracket PV is 0 is the same as to say that PV lies in this BNW. And remember, BN is just defined to be the image of this D here. So so to say that PV lies in BNW, that's the same as to say that PV can be written as dW prime for some W prime in Wn plus 1. And so we're going to draw all these elements in this diagram here. This is usually the best way to keep track of steps in proofs of this type. So we had this V here in Vn, and then its maps under P. So this element PV here, PV is the same as dW prime. So we've got our W prime here, and the D sends this W prime down to that same element there. So remember that this sequence here, I followed by P, that's a short exact sequence. Okay, and so that means that I is injective, P is surjective, and the image of I is the kernel of P. But the key point that we just need here is just that P is surjective. Okay, so because this P is surjective, and we've got this W prime here, that means that we could choose some V prime here that's sent by P to W prime. That's just what surjectivity means. Yeah. So now, we've got this guys here and here. So we could think the next thing we could do, we could apply this D to this V prime, and that will go down here. And you might ask, well, is dV prime just the same as V? Well, it isn't, but it's kind of nearly true. So let's look at, we were asking whether dV prime is the same as V, or in other words, we want to consider the difference, V minus dV prime, and we were wondering, well, maybe that might be 0. It's not necessarily 0, but it is in the kernel of P, as we can see by this calculation here. We apply P to this V minus dV prime, so that gives us PV minus P of dV prime. But P is a chain map, so PD is the same as dP. Okay, so this term here, PdV V prime, can be written as dPV prime. But remember, PV prime is just W prime, so this guy here can be written as dW prime. So here what we've got is PV minus dW prime. But PV and dW prime are the same. That was kind of how we chose our W prime. So this difference here is 0. Okay, so we've shown that P of V minus dV prime is 0. Or in other words, that this V minus dV prime, that's in the kernel of P. But we're assuming again that this is a short exact sequence. So the kernel of P is the same as the image of I. Okay. So that means that V minus dV prime, that's in the image of I. So it can be written as IU for some U here. U is in UN. Okay, so we've drawn these kind of dotted arrows because V minus dV prime is IU, so V is equal to IU plus dV prime. So we've just kind of drawn these dotted arrows to indicate that, that you take the dV prime plus the IU, and that's equal to V. So this U at the moment, that's an element of UN, but we actually want to prove that it's a cycle, that it's in ZUN. Okay, we want to prove that DU is 0. So we're going to do that, but we're going to first think about I of DU. Now I, remember, is a chain map, so I of DU is the same as D of IU. And IU, we introduced U here by this property that V minus dV prime is IU, so we can rewrite this IU as V minus dV prime. And so that's dV minus d squared V prime. Now, remember, V was a representing cycle for the class B, so in particular dV is just 0. And then here we've got d squared V prime, but d squared is 0 everywhere. So both of these terms are 0, so we get 0. Okay, so that proves that I of du is 0. Again, we're assuming this sequence here is short exact, so in particular I is injective. So if I of du is 0, that means that du is already 0. Okay. So this U here is a cycle. That means we can it's got a corresponding homology class, square bracket U. Okay. Remember, square bracket U is only defined if du is 0, but that's what we've just checked. So this is okay. Square bracket U is a class in HNU. So let's look at what happens to I lower star of this class A. Well, I lower star, so to do I lower star, we just bring the I inside the square bracket, so it's bracket IU, which is bracket V minus dV prime. But remember, this dV prime is in Bn. Okay. And this square bracket, that's just cosets mod Bn. Okay, so the dV prime doesn't make a difference to the coset, so bracket V minus dV prime is the same as bracket V. But bracket V was B, right? And that's how we introduced V up here. And B is bracket V. So we've got that this I star A is equal to B. So I star A is equal to B. So B is in the image of I lower star, as we claimed. So we'll stop this video here for the minute. There's lots more parts of the snake lemma to prove, but we'll do them. We'll carry on in the next video.